So, our next speaker, the fantastic Paul Jones, who hails from the north of Wales. And Paul is going to be talking about infrastructure as software. So, Paul is a software engineer with a background in building and deploying microservice applications in enterprise environments. And he tells us that he's spoken at the last 2 European KubeCon events. It's pretty cool. So we ask our speakers to fill in a few random questions about themselves. And one of the questions that we ask our speakers is who they're most inspired by. And I loved Paul's answer. Paul's answer was great. Paul said Mr. Bean. And I read it and I had a little chuckle and I was like, what, really? And actually, what he goes on to say later, I think is really poignant and an absolute brilliant point to make. He says, actually, Mr. Bean is great because not only does he embody British values, but also he just goes to show that all you need is a can-do attitude and you can get by in life perfectly well. So, you know, Mr. Bean, what a fella. Anyway, back onto some serious stuff. We're going to be talking about infrastructure as software. So Paul says that this presentation is driven by a desire to emphasize the changing paradigm in how we deploy and develop infrastructure as a code. And he's going to tell us a whole load more about that now. So let's put our hands together in the traditional way, not, you know, normal applause for Paul.
I quite like the Icelandic
We'll do it
Clap.
later.
Cool. Hi, everyone. Thanks for coming. Yes, I am Paul. I'm a software engineer at Jetstack, based here in Bristol. And today we're going to be talking about infrastructure as software. So this talk is about evolving the paradigm for infrastructure provisioning and how we can transition from declarative infrastructure as code to imperative. There we go. So firstly, we'll recap some existing solutions for infrastructure provisioning and talk about how this can be done both declaratively and imperatively. We'll introduce infrastructure software and how this can be done programmatically, so how we can programmatically provision infrastructure. And then we're going to take a look at a couple of open source examples. So firstly, Pulumi, and then hopefully time permitting, the Amazon CDK, both from a perspective of cloud infrastructure and also their integrations with Kubernetes. So to start, what are the main principles of infrastructure provisioning solutions? So through idempotency, we want provisioning to be deterministic, continuously yielding the same results over multiple deployments. We also want an agreed, centralized, consolidated source of truth for the state of our infrastructure. We want the ability to reason about the desired and observed states. So this also facilitates concepts like the reconciler pattern to determine the state differential and rectify any drift. We want to be able to version the state of our infrastructure, enabling us to apply branching models and apply iterative changes and rollback. Through tracking changes, we can also create an audit trail representing mutations in the infrastructure's desired state. And lastly, testing our infrastructure ensures that we gain confidence that changes have the desired effect and functionality has not been compromised. When implementing these principles, most existing tools define infrastructure in DSLs or in YAML. So, canonically, we use infrastructure provisioners such as CloudFormation or Terraform. So, as many might know, CloudFormation is a first-party tool for desired state configuration management in Amazon. CloudFormation templates use JSON or YAML to describe the infrastructure resources within AWS. CloudFormation is a powerful tool, but its learning curve is quite steep when it comes to using more of the advanced functionalities and nuances. Moreover, it's specific to AWS, so we won't be able to transfer that skill to any other cloud provider. As well, we have HashiCorp's Terraform, which is again an open source tool to define infrastructure in declarative configuration files, however, supporting all major cloud providers, offering extensibility integrations such as deploying Kubernetes resources. However, both rely on some form of templating to represent infrastructure state. But is this really infrastructure as code? Are we maximizing our development experience and using all the tools at our disposal? So let's talk a bit about YAML and DSLs. I think it's fair to say that they restrict our capability to truly maximize our repertoire as software engineers. Whilst YAML is great as an assembly language to configure Kubernetes and other cloud native tools, it's not expressive enough to capture common requirements and leads to significant boilerplate and copy and pasting. Due to this, there are a few DSLs like Helm, KSonnet, and Kustomize to help avoid this. However, this kind of exacerbates the issue, as that's just another layer of cognitive overhead to the development experience, having to learn nuances and maintain behaviors of another tool set. So YAML's strength is in structured data. Where it can go wrong is where we use YAML to describe behavior. Variables, arguments are not structured data. This is programming masquerading as configuration. We've met these concepts before, so why are we trying to invent imperative programming? Due to the constraints of templating languages, there's a distinct lack of features. So we can't do things like looping constructs, object-oriented principles like inheritance, abstraction, recursion, threading, automated testing. These are all absent. So again, that's inhibiting our developer experience. So evolving the paradigm. So as software engineers, what we really want is infrastructure as actual code. We want to use the same language we already know, use the same frameworks, use the same build systems and test systems, extending and complementing our current developer experience. We want to leverage everyday features such as TDD and reuse the development skills we already have. We should be able to use abstractions to generalize our code and make reusable components. We should be leveraging the open source community on our projects and combine our application code and infrastructure code to build consolidated, cohesive, deterministic repos. So, enter infrastructure as software. This is the practice of programmatically defining infrastructure using familiar programming languages and tool sets. So this is born out of the rapid pace of cloud-native development, combined with a shift to ephemeral infrastructure and the consolidation of application and infrastructure code, which demands a different view of cloud development. So knowing languages such as JavaScript, Python, Go means we can start codifying our infrastructure. It removes one of the biggest barrier to entries around infrastructure as code, which is another language or tool set to learn and maintain. Unlike Terraform or CloudFormation, we don't have the cognitive overhead of reasoning about resources in another syntactical representation, and resources are instead first-class citizens in the language of our choice. Furthermore, this is what we're representing infrastructure as actual code. This is easy to have standard practices such as TDD and use frameworks we already know. The lack of testability in infrastructure is something that's bugged sort of users of Terraform and CloudFormation in the past. And whilst there are solutions, they're not sort of feature-rich in comparison to native programming languages. So, adopting this approach, we can first leverage software principles in infrastructure composition. Language features such as inheritance, abstraction, encapsulation, recursion, looping constructs, and error handling can immediately power up our capabilities and productivity. We can gain tighter controls when it comes to governance of our cloud environments, and having resources specified in application or libraries means that we can more granularly check and control what code and thus state changes are happening before they're pushed through our pipelines. We can take advantage of static analysis and linting of our code, and even do test-driven development. We can have a coexistence between infrastructure and application code, where event-driven applications whose deployment and execution are all encapsulated in the same source code. We can also improve testability through the lifecycle of our cloud infrastructure, exercising varying echelons of testing, so we can go all the way from unit, component integration, and service-level testing for infrastructure. So this ephemerality is often characterized as developers moving down the stack and becoming responsible for the infrastructure, and operations moving up the stack, which is sort of responsible for the code. But the reality is the overall shift is towards increasingly codified provisioning and short-lived infrastructure. To support this shift, enterprises need tools that can connect application code and infrastructure code together in a logical, expressive, and familiar way, such that development and operations teams can apply increasingly changes and infrastructure resource requirements for cloud applications. So, in this area, we've seen a couple of existing tools. So first of all, we've got Troposphere. This is a Python library for creating CloudFormation as Python code that can be rendered into the appropriate YAML or JSON templates. And similarly, GoFormation. This is orientated around bidirectional transformation of Golang infrastructure to CloudFormation templates. Also, Cloud SDKs. They facilitate common languages to define, configure, and deploy cloud resources across cloud providers. What's actually lacking from these solutions is the life cycling of the components. While we can actually express resources as, in this case, Python, we're actually missing that deployment stage and maintainability in our cloud environments. It's important to realize that these libraries give direct access to the cloud APIs, and then though they can be used to provision resources, they leave it up to the programmer to do so reliably. Because these are imperative libraries attempting to programmatically provision and update infrastructure, using them can be error-prone, resulting in bespoke homegrown provisioning systems. So, our first example is a framework called Plumie. So, Pulumi is an open source project providing infrastructure as code through multi-cloud and multi-language cloud development platforms. This supports JavaScript, TypeScript, Python, and Go with SDKs for AWS, Azure, and GCP, as well as Kubernetes. The Plumie development kit platform also is a combination of tools, libraries, runtime, and service that delivers a consistent development and operational control plane for cloud-native infrastructure. Pulumi's programming model extends across infrastructure, managed services, containers, container orchestration, and serverless technology areas with full APIs for those services exposed, which can be targeted by any of the chosen languages. We can build libraries of code packages which implement standard policies, network best practices, and abstract resource configuration away from downstream services. So just to jump straight into a couple of examples. We have libraries for each of the cloud providers. So like I say, Amazon, Azure, GCP, and Kubernetes. So firstly on the left, we've just got a simple example of an EC2 instance being defined in the AWS library. We can create resources which are represented by objects with configuration defined through the instantiation. Similarly to Terraform and CloudFormation, we can export and import values between stacks, enabling portability and sort of dependencies between stacks. More on Kubernetes later, but on the right, we've just got an example of creating some resources in using one of the libraries there, and this can be deployed to any Kubernetes cluster that we've got in scope. We can also define event-driven applications where infrastructure and business logic can coexist and work together to form powerful, cohesive serverless applications. Plumie also provides a cloud-agnostic library, so we can deploy infrastructure to any cloud-native environment, abstracting away the underlying cloud implementation, and facilitates the application to be cloud-neutral, portable, and therefore driven by business logic, instead of stating any cloud-specific provisioning. This creates the relevant sort of resources in the pertinent environment, which is sort of configured externally to this code base. So Plumie supports multiple backends for storing its state. So like Terraform, there's two primary kinds, which firstly are web, which its backend is accessed by the CLI and used via REST calls, and then the file system as well, which where the backend is stored locally. The web backend stores checkpoints securely, and the CLI always communicates directly with the cloud providers using client-side authentication, and all state is encrypted at transit and at rest. So to compare Pulumi to other tools, so Terraform is the closest comparison to Pulumi. So like in Terraform, when we declare infrastructure in a DSL, the Terraform engine takes care of the provisioning and updating of the resources, which is very similar to how Plumie functions. The major differences between Terraform and Plumie are the use of languages. Obviously, with Terraform, we're using HCL to declare our resources. And like I said before, Plumie's rich sort of language support in JavaScript, Python, and Go. The features, so obviously because we're using real languages, we can do things that I was talking about before, such as looping, functions, classes, abstraction, all these sort of object-oriented principles, and create some libraries. And also Plumie has deep support for cloud-native technologies like Kubernetes, and supports advanced deployment scenarios which cannot be expressed in Terraform. In regards to CloudFormation, again, we've got the added advantage of being in familiar languages to us instead of sort of bespoke templating solutions. So we haven't got any sort of crazy joins or nested stacks, which is sort of imitating abstraction. And obviously Pulumi is multi-cloud, so we don't have any sort of vendor lock-in when it comes to just declaring all our resources in CloudFormation. In regards to the Cloud SDKs, again, you've got sort of multi-language support with that, but as I said before, you don't have the support of kind of life-cycling your components in that deployment phase and reasoning about sort of state drift as well. That's all kind of relied upon the developer to actually manage that life-cycling. So as I said before about the Plumie cloud, so this is a framework within Plumie for building container and serverless applications in a cloud agnostic way. The cloud framework is in preview and provides abstractions that allow us to write cloud applications for many different cloud providers using a common API. This is an abstraction package that defines APIs common to all cloud providers. And because these abstractions allow us to operate over different cloud platforms in a consistent manner, the low-level functionality and capabilities of the individual platforms are intentionally not exposed. So just in this example, this allows us to write cloud-agnostic code, which through external configuration can be used to deploy to multiple different cloud providers, yielding the same functional results. So here we've got a service type, which expresses a load balanced container, which can be targeted to run in multiple cloud providers, and also an API type, which is sort of expresses just a simple serverless sort of HTTP endpoint. This package also offers data abstractions, so with cloud agnostic resources like tables and buckets, which manifest in the relevant backend resources in that pertinent cloud environment. So for Kubernetes, Plumie provides an SDK that allows us to write Kubernetes applications in the language of our choice and is designed to fit anywhere Kubernetes is already being used. There's API parity with Kubernetes, so users don't have to learn a new API when writing Kubernetes applications in Plumie. It's compatible with existing Kubernetes YAML and Helm charts and is a drop-in replacement for kubectl. Theoretically, anywhere we have a kubeconfig file, we can use Pulumi. And in addition to being compatible with all existing Kubernetes resources, Plumie also provides advantages over the bare kubectl. So Plumie provides proactive reporting on resources, errors on resources failing to initialize. So if Plumie understands why the resource has failed to become healthy, it will tell us at provisioning time, therefore no debugging deployments to find out the root causes of failures. Again, like I said, it's got drift detection. So Pulumi can determine the diff, which means that it's always easy to detect when resources are out of sync with the specification in version control. There's precise lifecycle tracking. So like Terraform, the planning phase tells us explicitly what resources will be updated and deleted. And end-to-end planning. So Pulumi planning features also allow us to change, so the changes will propagate through apps. So for example, if we change a config map in Kubernetes, it will also cycle the pods that have dependencies on that config map. There's strong integrations with the managed Kubernetes offerings. So it's easy to provision managed clusters in sort of Amazon with EKS or GKE. So using this provision cluster, we can also create Kubernetes in that same sort of deployment. So we can go sort of end-to-end deploying our applications as well as the resources that they rely upon. And lastly, the Kubernetes SDK also supports deploying Helm charts, either through chart repositories or assuming local charts on the file system. So let's take a look at some examples. So like I said, the full API is available just in code, not YAML. So akin to normal Kubernetes resources, a deployment specification can be declared with the resources as first-class citizens in our languages. Here we're just creating a simple Nginx deployment with a service of type load balancer, and the load balancer's hostname is then exported from the stack. So initially we're just creating the deployment type here, and then we create the service, and at the end, like I said, we kind of export the front-end endpoint. So this example, so we run Plumie up, which is similar to Terraform, and then that will give us a preview of all the resources that will be created. And then it'll go through the full life cycling so we can see the resources actually deployed into the cluster. And Plumie will then just check the health of those deployed resources and give us that success. As you see that again, so creating resources, and it just waits for the readiness probes to complete, and then that's all good. So abstractions, apologies if you can't see that at the back, but I'll talk through it. So taking the kind of canonical Kubernetes guestbook application, we can refactor this in from a verbose set of resources and take advantage of being an environment which is conducive of abstraction. We can recognize a common pattern for a deployment followed by a service to expose that container, optionally behind a load balancer with a stable IP. So in this example, we're just calling the service deployment object 3 times with a container image and ports to expose that on. So it's just a simple kind of reproducible pattern. And then under the hood, we've got just this service deployment class. So again, this is just taking standard principles of creating a deployment and a service and taking the kind of constructor arguments to create the, use that image and sort of the endpoints that we want to expose. So running Plumie preview shows us the resources that will get created in our cluster. The end result of this is that we have 3 deployments and 3 services, with the front end being load balanced, which is the same as doing it with sort of the normal manifests. Obviously, this has been reduced sort of massively, so we've gone from approximately 147 lines of YAML down to about 20 lines of code. Not only that, but the code is much simpler to understand and easier to maintain. So I mentioned sort of managed services before. So Kubernetes integration can be taken further to provision clusters via managed services in cloud providers. Provisioning and managing and monitoring Kubernetes cluster is no easy task, and especially with Amazon using EKS, that can be a bit of a burden, and it's quite difficult to get running end-to-end in code. But through the Pulumi's EKS support, that massively helps with this task, and it can get a cluster provisioned using minimal code. So in this example, we're just standing up an EKS cluster. There is also this useful library that can kind of create some opinionated networking for us, so we can just use that as a basis for kind of the VPC and the subnetting where our cluster will reside. But the massive advantage of this is the transitive resources that gets created sort of behind the scenes for us. So in here we get the EKS service role, we get a new VPC and an EKS cluster, but this also launches the worker nodes in an ASG, which automatically join the cluster, which is normally a manual step that you have to do yourself. It installs a config map to the cluster, which allows the EC2 workers to join. It installs a storage class to the cluster, which allows the provisioning of EBS-backed persistent volumes. It also constructs a kube config for us. We'll talk about that now. And then optionally exports that to be used via kube control. As I said, these are all the resources that get created. So notice how we didn't have to create any other security groups or any of the networking components. It was just this one definition of an EKS cluster. On the export side of things, so we can reference from the CLI the exports from that stack and just pipe that to our kubeconfig file. We can use that in our CLI, and we can access the cluster that we've just provisioned. Note that we didn't need to populate the kubeconfig with any IAM credentials, as this was all injected by the EKS library into the config object when the cluster was provisioned. As I mentioned, there's support for Helm as well. So this significantly reduces the amount of boilerplate code required to deploy to Kubernetes, deploying from chart repositories or local charts on the file system. The TIL service is not required, but that doesn't matter as of Helm 3, obviously. But as Plumie will expand the Helm chart and submit the expanded YAML to the cluster for us. Here we're just deploying a simple Jenkins chart from the stable repository and exporting properties from the created resources. So what we're going to see now is Plumie up, and this will just sort of take that local chart and go end-to-end with our Jenkins deployment. Hopefully. There we go. Sorry, it's a bit small, but we're just seeing all those resources being created. So this is being deployed straight to our cluster. Again, it's just waiting for the pods to come up and the deployment to go healthy. And at the end of this, we will export the front-end URL for the Jenkins deployment. And via that, we can open that endpoint, and then voila, we hit Jenkins. In terms of serverless, one major advantage for having infrastructure as software is that the serverless offerings like Amazon Lambdas and Azure Functions can be just real language Lambdas. Serverless offerings today divide the experience between the infrastructure components, which is everything we're doing to configure the Lambda runtime, and writing and maintaining the code that will actually execute in the function itself when triggered. Because we're using general purpose languages, we can create resources and then wire them up to event handlers, just like normal event-driven programming. You can create event sources and handlers in the same program, choosing to wire functions up to existing resources. The optimum ways to do this is to create functions in line, and this blurs the line between infrastructure and application logic in a way that makes programs feel first-class distributed applications. So a couple of examples. Here we can see kind of on-put and on-event methods being used when resources are registering event handlers. So for the most part, any code we write here will work, unlocking all sorts of powerful composition scenarios. Underneath those onX methods, we have sort of Amazon resources transitively being created again, such as IAM attachments to facilitate invocations of the event-driven workloads. So again, we're just creating buckets and queues, and then saying when sort of a new event happens, execute this sort of workload. Just on testing, so why should we actually be interested in testing our infrastructure? Well, firstly, it increases our confidence in any changes introduced to our infrastructure. It provides resilience and security and demonstrates a left shift to addressing code quality, security concerns, and environmental consistent deployments. Through these varying levels of inspection, we can have varying options available to derive assertions of functionality and conformance to SLAs, security criteria, and best practice. As we see, there's a broad spectrum of infrastructure testing options available, but Plumie complements and expands on these mechanisms. As we're able to use sort of real languages like JavaScript, Python, TypeScript, and Go, we can use the full power of each language, which is available at our disposal, including all access to tools and libraries for that runtime, including the testing frameworks. Obviously, because we may have libraries and sort of classes and functions, we want to test them or even do TDD. So doing this the same way as writing any ordinary unit test against a program in our language. Here we're just creating an EC2 instance with a security group and associated ingress rules. Once we set this up in our environment, we can assert against attributes therein. Here we're just making sure that each resource has tags and that they actually contain sort of the name tag, just to kind of make sure they adhere to our sort of best practice. Also, we can make assertions around the security of our code and assert that they're conforming to security best practice. Here we're just searching the ingress rules associated to the security group and making sure they don't allow overly permissive SSH inbound access. So, after taking a look at Pulumi, what conclusions can we draw? So firstly, the cloud agnosticism feature provides flexibility and portability. It means that we avoid vendor lock-in, and in some cases, we can run our stacks in multiple providers by changing external config and not actually touching the underlying source code. The coexistence of infrastructure and application code yields more cohesion and event-driven workloads. And again, the Kubernetes cluster provisioning using managed services integrations reduces the cognitive overhead and code footprint and management of the resources down to a minimum. Programmatic generation facilitates more granular control and inspection of infrastructure resources. And obviously, lastly, the abstraction aids standardization across organizations through the reuse of downstream consumers. Let me do a time check. Do you know? Sorry, 7, okay. I'll rattle through this. Yeah, that's fine. So we just take a look at the Amazon CDK. So this is the Cloud Development Kit, which is an open source development framework to define cloud infrastructure in code and provision it through Amazon CloudFormation. So the CDK is basically a wrapper around CloudFormation, which abstracts CloudFormation definitions of AWS resources into an object-oriented library. We can think of the CDK as a cloud infrastructure compiler. This provides a high-level class libraries called constructs that abstract AWS cloud resources and encapsulates AWS best practices. Constructs can be integrated together into object-oriented CDK applications that precisely define our application infrastructure and take care of all the complex boilerplate logic in between. We can then run our CDK application, which is compiled into a CloudFormation template, which acts like an assembly language for AWS cloud infrastructure. The template is then ready for processing by the CloudFormation provisioning engine for deployment into our environments. Again, because CDK supports object-oriented languages, we can utilize language features such as looping, abstraction, and inheritance. So as I said, it's available in TypeScript, JavaScript, Java, .NET, and Python. This allows us to write libraries and applications in these languages and synthesize the stacks into CloudFormation templates, then deploy the stacks into AWS environments and diff against deploy stacks to determine any drift or impact of changes. So just to get started, you can run CDK init, and that will create sort of a sample project for us. As a quick start, here's a couple of examples of how constructs can be instantiated with resource configuration passed into constructors. Here we're just simply creating an SNS topic and an SQS queue, and then kind of having some composition between the two of subscribing to those resources and exporting some attributes therein. Apologies if that's a tiny font, but when we run init, we actually get a drop-down of all the available commands for us. So we've got CDK synth, so this will take our source code and synthesize it into a CloudFormation template. We can run some basic tests on that using sort of unit testing frameworks like PyTest. Then we can run CDK deploy, so that will take our source code, synthesize it into a CloudFormation template, and create a change set, and then deploy that to our environment. And then once we've actually deployed that to our environment, we can run CDK diff, again, like Terraform and things that show you kind of state differential between kind of observed and desired states. Here we've just got a simple example of a construct. So far left, we've got an application which invokes a stack. Within our stack, we can create resources, again, SQS queues and SNS topics, for example, but then we can invoke our construct. So this is just our custom object where we can sort of create a loop and just create some buckets or any resources, but this can obviously have sort of open-ended functionality. I'm just going to skip to one message I want to say at the end, so apologies. Get there in a minute. It's just about cultural readiness, so kind of the philosophy of going down this kind of codified route for our infrastructure. So when seeking to shift the paradigm for infrastructure composition into programming languages, we first need to take a look at the surrounding culture in which this is being adopted. If there are DevOps silos or a distinction between infrastructure platform and development, then introducing a principle which essentially blurs those lines needs to be carefully considered. Whilst it might be acknowledged that there are distinct benefits to shifting developers down the stack and ops up, this might actually be detrimental in a culture which is not ready for multidisciplinary teams in the organization. Full disclosure, I stole this slide, but I think it epitomizes this sort of adoption brilliantly. Depending on the cloud native maturity of an organization's culture and technology offering, there may be certain prerequisites required before leveraging the value of ephemeral environments and codified cloud resources. There is an evolution through the cloud native maturity paradigm, and we must have stable foundations and have invested and culturally appreciate the stages of our evolution. Without this, we won't maximize our potential nor deliver the full value of running in a truly cloud native environment. Cool, so just to wrap up really quickly, hopefully this has shown the benefits and justification for moving infrastructure into a more imperative style and how we can change the paradigm and how this can be achieved. We have the tools to evolve the paradigm for infrastructure composition, which facilitates a coexistence of application and infrastructure code, thus resulting in more testable infrastructure. This reduces the cognitive overhead of having to reason about DSLs and YAML to kind manifest our resources, and this leverages modern programming languages to programmatically define these resources. As application code and supporting infrastructure become more and more blended, it's natural that software developers take on responsibility to define both. The next logical step is that we have the same languages, tooling, and practices for both software and infrastructure. And with that, I think I'm done. Thank you very much.
I'm here.
Hello.
Well done, Paul. And we gave you a traditional clap, so excellent. Thank you. Okay, folks. So we have a good bit of time now for some questions. If you stay in this room a few times, you'll hear this little spiel. Q&A sessions are about questions. We really don't want to get into debates or discussions or thoughts from the audience at this point. If you have those, come and talk to Paul at the end. I think he'd love to hear them. He'd love to have a chat with you. But for this particular session, we'd love your questions. So, do we have any questions from the audience, please? Okay, so we have lovely Lizzie here, Lizzie with the roving mic. So Lizzie's going to trot along to you now, and if you could talk nice and clearly into the microphone so we could all hear you, that would be awesome. Thank you.
Yeah, thanks for the talk. The question I had was if you're using something like Plumie, but behind it you're using, say, AWS.
Yeah.
Is it a safe assumption to say we could just start using Azure with very little change, or are there pitfalls to be had in thinking you can use Plumie to swap cloud providers?
Yeah, so the portability between cloud providers, there would be some like underlying code changes. Like I showed, there's that kind of cloud agnostic library. So that actually you could port between Amazon and Azure and still have the same source code that would manifest in the same resources. But there would be an activity of kind of changing your Pulumi code to work in both clouds. There are kind of specific libraries for those providers.
So is it the case if you opt in to use, say, an Azure specific library, then you already know that there might be issues with going to AWS with that?
Yeah, there would be a kind of a migration effort to kind of, you'd have that code base. There would be nuances, right, because the kind of the APIs and the resources don't one-to-one map.
But in the for the neutral library, you'd be fairly
trivial. Yeah, well, that's exactly the point. Yes, you have external config to say this is the environment it's going to, whether it's Azure or AWS. But your source code should work the same. It should be interoperable at that point.
Okay, thanks.
Brilliant. Do we have any more questions? Don't be shy. We're very friendly. Lizzie, we have one down here in the front. The wonderful Lizzie is making her way to you as we speak.
There's almost, it seems like there's like new cloud services from AWS, Google, Azure almost weekly. Yeah. So I imagine it's quite hard for these frameworks to keep up. So if you're looking to use some of the new features from one of the cloud service providers and leverage some of this stuff, how can you do those things together?
Yeah, I think so. On that, I think they're obviously iterating as fast as possible to keep pace. And obviously, we've seen with CloudFormation that doesn't really keep pace with what their offerings are. So I think there is an effort there to keep up with the sort of resources that you can deploy. On that note as well, kind of the parity between SDKs and the language supports. So from my findings, the kind of JavaScript, TypeScript libraries are much further ahead or much more mature, I should say, than the Python and the Go libraries as well. So yeah, there is a conscious effort to kind of keep pace, but from a developer's perspective, that can be kind of like a little bit frustrating if they're not quite at the cutting edge of it. But yeah, especially with CDK as well, you're going to have things, if it's not even in CloudFormation, it's definitely not going to be supported in the CDK sort of libraries. So yeah, there is that issue. Does that answer your question? Yeah.
Oh, hang on. We'll just bring you the microphone back so everyone can hear.
Is there a way, if it's not yet supported in the framework, is there a way that you can use both at the same time? So you can use some CloudFormation and Plumie? Or does that get really hard and painful?
I think the only thing that springs to mind is that you would have some kind of bespoke, you could still use Boto at that point, couldn't you, to hit the API and then create those resources if you needed to, but then you'd have like some kind of, CDK or Pulumi code, and then that would have, functionality or interaction with your custom stuff that would create those resources, and then you'd port that over, I guess, at a point where that was actually supported in Pulumi. So yeah, I don't think it's kind of natively supported, but sort of a hybrid solution would be a bit messy.
Awesome. Okay, more questions. Anybody else? Don't be shy. Okay, Lizzie's on her way. We might need some audience participation here to get that microphone to its intended recipient.
Just a quick question on you touched on security and how it embodied best practices. Are those kind of opinionated and buried in the implementation, or if you've got different requirements, can you get at that and change it, or how does that work if you've got?
Yeah, so there's a different perspective there. So you've got a few libraries that will kind of stand up some opinionated security stacks. So like it'll create some VPCs and security groups for you, and kind of have some opinionated stuff. So it won't create like open ingress and things like that. That's one thing in Pulumi specifically. I think when it comes to network security and things, that's very much on you, and that's kind of enforced in your code base. So you saw the kind of unit tests there. That's checking that compliance is actually being adhered to. So in theory, you'd have some like CI/CD pipeline that would actually assert that they're conforming to security best standards. But I think that's like one of the major advantages of having this in code is that you can actually create those rules. So if you're doing it in CloudFormation, for example, there are tools out there. There's like CFN NAG and CFN, I think it's Ripper or whatever. But basically, you can define some like custom rule sets that will lint your template. And ensure that you're not that you are conforming to like security best standards, but that's quite kind of heavyweight. Whereas you can actually have like security testing frameworks that would assert that that's actually conforming. So yeah, I think that's a major advantage of it going to code. Within the CDK specifically, there are some kind of things you can apply in there to actually enforce like security best practices as well. So that is in support, like that is in scope as well when you're actually defining like some like VPCs and subnets and things. So yeah, I think that the support is baked in as well to those libraries.
Brilliant. Any more questions? We do have a bit more time, so we can do more questions. Oh, sorry, I didn't see you there. Paul was in the way.
It's not a problem.
Go for
thanks
it.
for the talk. Really interesting around the sort of serverless side of AWS and kind of AWS specific question. In terms of the drift detection, does it manage migrating existing resources into CloudFormation that kind of CloudFormation wouldn't, and would say delete your Dynamo table and all its data?
Yeah, migration's a bit tricky. So there's multiple parts to that. So with Plumie specifically, you can adopt existing resources, and then that can be taken under Plumie control. It is a bit tricky though. Yeah, you're right. You can get into situations where during that migration, sort of that's been taken out of scope for that CloudFormation sort of ownership model. So it is a bit difficult, but yeah, there is built-in functionality, specifically in Pulumi. I'm not too sure with kind of how you go from using CloudFormation to Amazon CDK and the ownership model there, but there is functionality within Pulumi specifically to assume current resources that are already deployed and bring that into scope.
Cool. Now, we haven't had many questions from up the back. You're involved too. You can ask questions, and we don't mind running the microphone up to you. So are there any more questions? Oh, yes. Okay, second round. Love it. Okay, bring it.
I think it adds on perhaps to the first question that was asked about the sort of cloud native elements.
Okay.
It seems that you could wrap some of those, some very sort of simple things and common use cases for queues and other things that could be very easily abstracted. So is there a community that's sort of building things like that and sharing, rather than everyone kind of reinventing the wheel where they've got, those common use cases? What's the kind of momentum behind?
Yeah, not that I've seen. So I mean, Plumie recently hit like 1.0, so it's relatively new. It's an interesting question. I don't know, to be honest. I mean, you would imagine that there would be kind of libraries out there that would sort of facilitate all that stuff, and similarly, like the constructs within the CDK. That is completely something that should happen. But I think people are going to have their own sort of nuances to that and their own kind of custom requirements. But yeah, in theory, you could have shared libraries that will create sort of all different resources in a sort of, and then you can adhere to like security best practices. Therefore, because that would be baked in.
Oh, hang on, we're going to bring you the microphone back. Do you know what? If you ask a question, just hang on to it till you're done.
Well, the nice thing about the fact that it's programmatic and an inheritance, that those shared libraries can be, nice low level, and then people can specialize on top of those. So it feels like the pattern is there for people to build some really nice reusable assets on top that can be shared.
Hang on a second. Are we getting away from questions here?
Oh,
I don't know. I'm going to give you the benefit of the doubt, but just
I retract that last statement.
Okay. I
Just-
didn't
no, just
hear
to
an
add to that, though.
inflection at the end.
'Cause I think, no, sorry. So, like, within an organisation, I can see it. There's a definite use case. So, in teams that I've been in, so kind of exposing, having a shared library where there is kind of an opinionated stack, and then developers can kind of like consume that downstream. I think that's a real powerful use case. So you're not having to reason about, configuring queues and configuring different resources. You can just kind of have that abstracted away from you, have that defined upstream, and then just import that library and use components therein. I think that's like a really good use case.
Awesome. Oh, one more question, but down the front again. Folks at the back, you're not representing. But we're very happy to have your question.
Thanks for the talk. So going back to like the CloudFormation, so on AWS you've got CloudFormation, and if something drops off the stack, it knows to delete it.
Yeah.
Unless my understanding is wrong, and it may well be, in Azure there's not the equivalent concept. So how does Plumie stateful in a way? How does it know when to drop something and delete it, or have you got a tab about it? Or?
Yeah, no, because it was similar to Terraform in that regard. I believe that, as I said, the kind of it's gone. But in terms of how Pulumi stores state, that's kind of like in the back end, obviously. And I think it'll just it'll basically scrape your environment. It'll just have a state file, basically. So yeah, you're right. There isn't that concept of like a drift or something's been deleted. But yeah, your state file would be different depending on if you remove something from your stack. So yeah, it would kind of therefore schedule a deletion of that resource.
That's it. Thank you.
Yeah.
Awesome. So we're going to take one last question. Lizzie, sorry, this is a tricky one for you, but she's on her way. So we'll take this one last question, and then we will break for refreshments.
This is hopefully a quite simple question about language support. So
Yeah.
I really value the idea that you can use the languages that you're kind of familiar with, but what if one of those is not one of those? Thinking from Pulumi, do you know if they're planning to support other languages, and to what extent can you add a new language, or could an organization or whatever add a new language support, for example, Clojure?
Yeah.
Is there kind of a separation between the back end part that's sort of doing the Terraformish work and the front end of it, so that you could abstract and create a new language on top?
Yeah. So they've been adding language support kind of iteratively. So recently there's been Go added and things like that, and the Python support as well. So I think, as I say, there is kind of a disparity between like where the maturity of those language supports. So I think it's fair to say like the TypeScript and JavaScript libraries are more mature than the others. But I think it doesn't matter at the end of the day. I think that other languages will come along, and it's kind of, as you say, it boils down to like what's actually happening underneath. That's written in Go. That's Pulumi's libraries. But yeah, there is sort of the upstream language support is just kind of just needs to be implemented just to work with that. So yeah, there will be like further support for languages. I think if there's enough of a sort of appetite for it, if there's enough demand, obviously, then yeah, they'll kind of support that in the long term. But I think obviously they've hit the big ones. More use case of Java might come along like it's in CDK, but yeah, in theory that there's nothing stopping other languages coming along.
Great. So there's some kind of separation between the sort of back end of it and the language layer.
Yeah.
Fantastic. Thank you.
Brilliant. You've been a fantastic audience. Those were great questions, and almost all questions too. So bravo. Let's have a round of applause for Paul. Thank you. Okay, and so we now come to our Icelandic Clap. Has everyone had a go at this now so far? Anyone not clued in on the Icelandic Clap? For anyone that isn't sure what it is, this is Nick's idea, by the way. But I'm growing. It's growing on me. The Icelandic Clap. We all do one clap together to show our appreciation to our speaker. So, and ideally above your head, if you can as well. So, on the count of 3. 1, 2, 3.